like to introduce the next speaker. Our next speaker is Dr. Bruno Batista Fernandes. He's a research associate in the Center for Subsurface Energy and the Environment in the Department of Petroleum Engineering at UT Austin. His areas of research include reservoir simulator development and application, enhanced oil recovery modeling, and computational sciences. Dr. Bruno, all yours.
Okay, you can see it, right?
Yes.
Okay, good morning, everyone. I'm Bruno Fernandes. I'm going to be talking about some of the CO2 storage work that we have been doing in our research group regarding sensitivity analysis, and we also are going to be looking into the faults, leakage stuff. So in this presentation, I'm going to first briefly introduce some of the challenges we have in the CO2 storage. Then I would like to discuss a little bit about the embedded discrete fracture model that we use, EDFM. Then I'm going to be presenting some sensitivities we did on the High Island Unit 24L, where we basically tested the effects of diffusion, here molecular diffusion, and how we handle the impermeable zones within the storage aquifer. Temperature and also number of wells. We did do some more sensitivities, but for the sake of time, this is the only things we are going to be presenting here. And we also are going to be looking into the use of EDFM for the fault reactivation, for a fault reactivation case study. So as has been discussed previously, right? Leakage is a big issue in the CO2 storage problem. We can have leakage through active faults, so the faults, they may be already active and able to connect different formations. And we may also have very high injection rates or high HP controlled wells that are going to activate or reactivate our faults, right? There are some other issues too, but we are not going to be discussing that in this talk. So we have realized that we can use the embedded discrete fracture method for also modeling faults. This is a method originally developed for fractures. And the way it works is we create some extra grid blocks for our each fracture segment that intersects one matrix block, right? So we realized that we can model our faults as modeling the fault zone. So we would have here a damage zone, and then we would have the core fracture, the core zone. So the core zone is where we actually use, create the EDFM blocks, but the damage zone is also modeled with the EDFM. And the reason we choose EDFM is because EDFM has high accuracy and flexibility while keeping the gridding easy, and it also has a high computational efficiency, right? So here we have an example of a Cartesian grid. It's a simple grid where we actually have a fracture here in a very complex direction. So we could, for example, use discrete fracture method here exemplified with an unstructured grid, but this would require some grid refinement along the fault. This is very challenging, especially for grid generation tools. Here we have a 2D case, but if we were to go for a 3D case, this would be very, very complicated. We could also use LEGRs, but this would maybe require very fine regions of the domain. And of course, we could also use DP for this type of purpose. But as you see, it seems and has been proved through time that EDFM is a very powerful tool for working with fractures. So for the first case, as I mentioned, I'm going to be presenting some of our sensitivities at the High Island Unit 24L, which is located at the Gulf of Mexico here in Texas, just 20 miles southwest of Sabian Pass. And we basically take our geological model for the High Island 24L, and we use the fracture planes into the EDFM preprocessor, which has been provided to us by Simtech. And the EDFM preprocessor is going to map the matrix blocks that are connected to the fault. These matrix blocks connected to the fault are going to give us our damage zone, and we can test sensitivity of the faults on it. So here we had 49 faults, and we used again EDFM for importing it. And for the run, we use SMG, and this is a great advantage of the EDFM tool, that we can use our in-house simulators, UTComp, UTCam. They are able to handle. They are designed to use EDFM, but EDFM is also done in a way that it can be used with commercial simulators such as CMG and Eclipse, and so on. So this is our CMG reservoir simulation model. We basically have some overlying layers above the cap rock that we added here. And below the cap rock, we have our storage aquifer, right? The storage aquifer has some low permeability zones. And because the permeability is low, what we do is we in the original model, they are treated as inactive zones, right? One of the things we want to test for our sensitivity analysis is if we do have molecular diffusion, then how this treatment for these impermeable zones are going to affect, because over these long periods of times, 1,000 years, we should have some diffusion into these impermeable zones. So for this case, we inject CO2 in this aquifer for 30 years, and the total simulation time is 1,000 years. So we can see how the CO2 plume is going to propagate, and in one of the cases, if this CO2 is going to leak or not through the faults. The maximum BHP was 3,400 PSI, and we actually had the injection rate of 0.5 megaton of CO2 per year. So again, for the sensitivity, we tested first sensitivity to molecular diffusion, and next sensitivity to the reservoir temperature. So we wanted to see what was the effect of molecular diffusion process, which is normally neglected, especially in the impermeable zones. How this would affect the amount of CO2 that is trapped that is stored by each of the different mechanisms, right? In the free mobile CO2 form, in the solubilized form, and in the capillary trapped form. So we also tested these sensitivities to two cases. The first case I'm going to be presenting now is for the sealed faults. So we use EDFM to seal the faults. In the second case, we are going to consider the faults to be open and leaky, so that there is a path across the cap rock, and we can see if CO2 will migrate. So here we have our 6 injectors, and here we have a view of the CO2 plume. The regions here that we see are only the regions where CO2 has reached it. And we can see here our base model without diffusion, without molecular diffusion, and with some cells being active. Here in this view, we have all the cells being active and some diffusion. And we can see that the CO2 has gone much farther in this case. And we can also see similar effect on the case when we look at the cross-section view. Now, if we look at the plots for example, here we have the percent change for each of the different cases we tested. So here, the yellow box, we have having the active cells, all the cells active, plus molecular diffusion, we have an increase in CO2, total CO2 stored of about 2%. So it's not a very significant increase for the total CO2 that we can inject. But if we look at what happens for each individual mechanism, for example, here, how the solubilized CO2 evolves over time, right? We're gonna see that the base case, and the case with all cells active, but not having molecular diffusion, we have no difference between them. But if we have all the cells active plus molecular diffusion, we have a huge increase in the amount of CO2 that is stored, that is solubilized. And on the other hand, we have a huge decrease in the amount of CO2 that is in the free mobile form, right? However, when we look at the amount of CO2 that has been trapped by capillary trapping, then we do not see much changes. If we look at the temperature now, we basically see here that if we increase temperature, we're going to reduce the total amount of CO2 that we can inject. And if we decrease temperature, we're going to increase the total amount of CO2 that we can inject. Now, if we look at each individual process for the solubilized CO2, as we would already guess, if we decrease temperature, CO2 is going to, we are going to have less solubilized CO2. If we increase temperature, you're going to have higher solubilized CO2. Now, for the free gas, we would have here basically the opposite. If we decrease temperature, then we have more CO2 in the free gas form, and higher temperature, we would have less CO2 in the free gas form. And here we just test a combination that would give us the best total CO2 stored, which it would be all cells active plus molecular diffusion plus decrease in temperature. Of course, we cannot decrease temperature. That's a parameter from the reservoir. Now we go for the next case where we look at the case with leaky faults. And now our EDFM blocks, they are gonna give us the path for this CO2 to migrate across the cap rock. And the effects are very similar for each of the processes, regardless of the faults. And also for this, for the cross section, the only difference here is that now we have even some diffusion through the cap rock. But now we can also look at the CO2 that has migrated. So although we do not see much differences in the CO2 migrated plume, we are going to look into more details in the amount of CO2 that has migrated later. So for the sensitivities, we have basically very similar trends regarding diffusion and also temperature, and even the total values, they are very close to what we have for the sealed faults case. But now, since the faults, they are leaky, we can look at the total amounts of CO2 that have migrated above the cap rock. Right, so what we have here is the progression of the CO2 mass that has migrated. And we can see here our base case, the black curve. And we have here our yellow curve, and also green curves here are the cases where we have the molecular diffusion. The green curve, we have all cells active plus molecular diffusion. And we can see that they reach a plateau in the total amount of CO2 that has migrated much earlier than our base cases here, and the cases that basically do not have diffusion, right? And if we look at total amounts after 1,000 years, we are going to see that here at the yellow box, we have less 30% mass of CO2 that has migrated when we consider molecular diffusion and all cells active, right? As we see for early times, this doesn't make too much difference, but as time passes, then we can have some large difference being made. And finally, for this case, we test the sensitivity to a different number of wells. So now we inject with a constant rate of 1 megatons annually, and the faults they are leaky. So we have the test with 1 well, 2 wells, 4 wells, and the case with 6 wells, which is our base case here. So here we have a plot of the cumulative injected CO2 over time of the 30 years period that we injected. And here we have a plot of the what I would call effective amount of CO2 that has been stored. So basically the CO2 is stored under the cap rock minus the CO2 that has migrated. And as we can see here, part of the best case at the end of 1,000 years was the case with 4 wells. And that is obviously related to how far these wells were from the faults. So we basically are trying to be as far from the faults as possible. And this is also telling us that for this specific case, you don't really need to have 6 wells, maybe 2 wells is enough. They just need to be in a better position to avoid contact with the faults. Finally, we go for our next case where we use EDFM for fault reactivation. And the way we can do that is we use EDFM tool to create some LEGRs close to our faults. And then we use some geomechanics to calculate our basically like compaction tables to have changes to change the properties from the fault zone, the both damage zone and the core zone. And here we have the first analysis with only one fault here. We have before activation and after activation, where we can see the pressure propagating over the fault. I'm sorry, not the pressure, the gas saturation, but also the pressure in this case. And here we have our next case, considering here 2 faults and injecting at the middle of the faults. And we can see over time, after 10 years of injection, after 50 years, and after 1,000 years, how the reservoir behaves. It's important to notice that in this specific case, if the fault is reactivated, it doesn't close again. So we can see how successful it is to use EDFM for this type of problem. So finally, we used EDFM to model the flow through leaky faults and also to model the reactivation of faults. There are many different ways of using EDFM, to be very honest. For example, now we are using EDFM for reactivating faults, but the reactivation is really being done by geomechanics itself, rigorous geomechanics, and we can also see that the effects of the molecular diffusion, they were very significant, especially when we consider all cells to be active, even the low permeability regions, right? The sensitivities, the sensitivity trends, they were not affected whether the faults they are sealed or not. And the CO2 migration has been observed to be lower when we consider molecular diffusion. Of course, all of this, we also need to do some study of grid refinement and see if that One of the reasons we consider only molecular diffusion and we do not consider physical dispersion in this case is also that we would consider that, okay, there is enough numerical dispersion in the model. So I would like to thank Simtech for providing us with the EDFM preprocessor tool, CMG with the licenses for GEM, also ExxonMobil for the funding of the High Island 24L model, and also Tavasoli et al. That provided us with material for the fault reactivation. So if you have any questions.
Yes, thank you, Dr. Fernandes, for your presentation. We do have some questions. The first one says, have you done any geochemistry sensitivity modeling during CO2 injection to see the effect?
No, this is something that we are still preparing. After we finish preparing the model with geomechanics, having fault reactivation, because we want to see if sensitivities to fault reactivation on the High Island 24L, then we are going to be looking into that.
Okay, and we have another one. What are the main mechanisms to cause leaky faults? Do natural fractures around faults play a key role?
Yeah, they might play a key role. We might have these fractures here connecting the, if they are reactivated, right, they might connect the fault to the fault core. So we can have, in fact, we can do all of this study with EDFM. We could put a natural fracture network and have the natural fracture reactivation. You have seen before that this has already been done with EDFM, basically reactivation of natural fractures.
Okay, Mauricio, do we have another questions from the Teams group?
We have one question from also from the Zoom. It says, what software did you use to conduct the sensitivity analysis? Additionally, which model do you use, back oil or compositional model?
There was, I'm sorry, I lost the first part of the question.
What software did you use to conduct the sensitivity analysis?
Okay, you mean we use the CMG gem, and CMG gem, as far as I recall, it uses a gem res with an ILU preconditioner. We do know that for cases with fractures and these high permeable channels, it is normally good to use CPR solver, but you know, CMG doesn't really have it, and we were using CMG for the project. So maybe if we were using Eclipse or Intersect, we would use CPR for this type of case. Now regarding the second question, we do use a cubic equation of state for this case that has been tuned by one of our previous students to be able to handle CO2 and water, right? So it is, he basically calculated, I'm sorry, he fit some experimental data for viscosity, and so viscosity, binary coefficient, binary interaction coefficients, and also density, I'm sorry, volume shift to account for corrections of CO2 solubility and all of that with respect to temperature and reservoir salinity.
Thank you. Finally, was there any criterion or evidence in your study to assign which fractures were reactivated and to define the degree of fault transmissibility?
Yes, we used some geomechanics simplified calculation. You can actually find the calculation on this paper.
All right.
Okay.
Thank you, Dr. Fernandes. Professor, could you continue?
Are we ready for? Thank you very much, Dr. Fernandes. Appreciate your presentation.